Welcome everyone to the pre-recorded lecture for Solid Earth Geophysics course on 13th of November 2020. And we have been discussing about exploration seismology or reflection seismology. And this is where we stopped yesterday. We said that this is the raw data that is being acquired by different seismic survey techniques, which we discussed in the previous class. And then we said that such data actually goes through steps of processing, and then we finally get a picture which looks something like this, ready for geological interpretation. So this is more or less is how the subsurface looks like. It might not be 100% perfect, but this is the closest that we can get from this data. Of course, the features which are below seismic resolution. So there is some sort of resolution for seismic data, which could be around 20 to 50 meters in today's world. So anything below the seismic resolution, you will not be able to image that or resolve that with the seismic technique. So that is another drawback or a challenge. Okay, so if something is maybe less than 20 meters or so, then you will not be able to distinguish that with a seismic technique. For example, if you have a fault which has a throw or displacement less than 20 meter, you will not be able to catch that one up uh, in a seismic section. So today our topic of discussion will be essentially how to process this data. So what are the steps that are taken by which this data is essentially transferred to something like this. Now, seismic processing, of course, is a very complicated technique, and there are uh, courses designed along it. You need to have a good algorithm base. You need softwares, so on and so forth. But our job today is to just learn about the philosophies, what is the physics behind the processing, and that is where we would stop. Later on, if some of you want to work on seismic processing, you will learn more about the technique, how it is practically done. Okay? Today we are going to discuss about basically the philosophy. Okay, now again, let us explain seismic processing with uh, a real life example. And the first step is called shot gather. Okay, so what is done in shot gather? So you can see here that this is a offshore seismic survey that is going on. There is one source which is denoted by S1, and there are five receivers. Okay, you can see the source, from the source the acoustic waves are being sent, which is kind of reflected at the interface 3, and then being received by R1, R2, R3, R4, and R5. The corresponding ray paths are actually designated by the dotted blue lines. Okay, so that is the reflected wave that would help you to image uh, 3, interface 3. Okay, so as a result, what I can see with the same philosophy that I have explained, between S1 and R1, the two-way time will be minimum. Between S1 and R2, the two-way time will be bit more than that. Between S1 and R3, of course, the T1 time will increase, and the maximum T1 two-way time will be between S1 and R5. So hence, I will get the traces corresponding to R1, R2, R3, R4, and R5 would look like this, where the blue color represents the positive amplitude, and the white color or the colorless part is the negative amplitude, which stands for compression and relaxation that we talked about. Now, that is not the only wave which is reaching R1, R2, R3, R4, R5 in this particular example. what else is also reaching are the direct waves. That means you are creating a disturbance at S1, and then anything, the wave which is not penetrating through the subsurface are directly reaching to the receptors, right, through this media. In this particular case, the media is water. Okay, so the wave is actually reaching R1, R2, R3, R4, R5. Of course, the direct arrival of the wave will be faster than the reflected waves. So hence that is being designated by these blue traces. Okay, so you can see that uh, each of these. So this reflector is kind of this reflector is kind of is represented by this say the series of wiggles or wavelets, and here we can see that the direct arrivals are designated by these wavelets. Okay, now let us say we are now only focusing on this particular point. Okay, let us say we are now only focusing on point number x, okay, which is between S1 and R4. For example, okay, we are now focusing on this particular point. So, so that let us say that okay, that point I have demarcated it with X. Let's put the right nomenclature. Let's say this is A. Okay, this is the point A. Now we are looking at point A. Okay, again we are looking at point A. So what we are seeing at point A, if we have multiple source and reservoir receptor pair, say for example S1 R1, S2 R2, S3 R3, S4 R4, S5 R5, this point A is imaged by all these source and reservoir pairs, right? So there is acoustic wave signal is sent from S1 is being received by R1 when it is getting reflected at R1, okay, when it is reflected at point A, and similarly from S2 to R2, similarly from S3 to R3, similarly from S4 to R4, and S5 to R5. So that means this single point A is actually imaged by all these source and reservoir pairs, okay. So but then, of course, uh, with the same logic, for S1 R1, the travel time, the two-way travel time will be least, and for S5 R5 pair, the two-way travel time will be maximum. Okay. So now this particular point A is called a common midpoint. Okay, this is called a common midpoint. Now, what I am observing that for this point A, okay, so these are like all the receivers R1, R2, R3, R4, R5. Okay, so and so on and so forth. You can have even more. So here the offset distance is plotted. Okay, so offset distance means, say for example, this is the distance between S1 and R1. Then the distance between S2 and R2, the distance between S3 and R3. So the offset distance is plotted. Okay. And then, of course, that the travel time essentially will increase with the offset distance, right? More the offset distance, I have more travel time. That is what you will see, right? Because S1 R1 will have least offset distance, S2 R2 will have slightly more offset distance, S5 R5 will have the highest offset distance. Of what is offset distance? We talked about it, is the distance between the source and the receptor, right? So S5 R5 has the maximum offset distance. So if we put plot x in the x-axis offset distance and in the y-axis true wave travel time, we see with offset distance the true wave travel time is also increasing. Okay. Now, but all these wiggles, all these wavelets are actually imaging point A, right? So they are imaging point A, and they are going through the same media first of all, but covering different distances through same sort of media. And the other important thing, the seismic velocity at corresponding medias will be the same. It's only the distance which is different for all these wiggles to actually occur. Okay. So now what you can do, then there is a process that you do what we call CMP gather. So the travel time differs since the path for near offset trace is less than the path for the far offset trace. With the correct velocity, we can correct the difference in travel time for each trace. Okay. So this curvature, that is essentially because with increase in offset distance, I have more travel time, right? So hence this particular hyperbola, this curvature is. Otherwise, it would have been a straight line simply because we are actually imaging the same point, right? So what I have to do now, I have to apply some sort of velocity. So the velocity, the correction will be least where uh, the distance is minimum, the offset distance is minimum, and the correction will be maximum where the offset distance is maximum. Okay. And then what my idea will be is to actually flatten this line. Flatten this line means then this will essentially be the single point. Okay. So now if we use the correct velocity, this line will be flattened. If we use a velocity which is too slow, there will be a curved down line. If the velocity is too fast, it will be a curved up line. Okay. So this is what we call, we have to actually gather them in a on a under a flat line. Okay. With the correct velocity, we can gather them on a flat line. Now what we would do, so this is where we started with the common midpoint technique, with CMP gathered, common midpoint gathered, and then I have corrected the midpoint gather, put them onto a flat line, and then what I would do, I would stack these stresses. That means I will overlap one trace above another. What that would do essentially, that would actually amplify the signal. Okay, that would amplify the signal. So, and that is what we call as stacking. So there are 10 folds are kind of stacked under one particular trace. Okay, 10 folds are now stacked under one particular trace. So we stacked several offset traces, and the traces are called is equals to fold in this particular case. The geologic signal will be additive. Okay, the random noise will be tending to cancel. Okay, so if there are, so by doing this stacking process, what I would do, I would actually increase the signal to noise ratio. Okay, so the more real signal will be enhanced and the noise will be cancelled. Okay, so I do my CMP gather. After doing my CMP gather, I do a move out correction, and this is what we call move out corrections. And move out correction means that I have to flatten my hyperbola to a straight line. Yeah, because the fact that the um, travel time is directly proportional to the offset distance. Okay, so this is what we call move out correction. So CMP gather, after that move out correction, putting them on a flat line and then stacking them together. Okay, and this is what we call stacking. Okay, so stacking is generally done to increase the signal to noise ratio. Okay, this is not important to have. So now, after we have stacked, Okay. After we have stacked, we get, after we have stacked, we get, so this is how it is. Okay. Let me just take one empty slide and then I'll explain what it is. So suppose this is my subsurface lithology. These are my different boundaries. Okay. And these are my CMPs, which are lying immediately above another on each corresponding interfaces. Okay. So what I am getting, I am getting a like a line. Okay. After I do my CMP stacking, I get traces corresponding to each of these common midpoints, right? Stacked common midpoints. This is what I am getting. And this is the picture which is shown here. The picture which is shown here. Okay. Now we have, imagine now we have several traces like this. We have several traces like this. Now there is something, another step which is done. So the first step we talked about is CMP gather, then move out correction, then stacking, then the next step in processing, and that is what we called as migration. And let us try to understand what migration is all about. Okay. Now let us say that my common midpoint, so my reflector is like gently dipping, and this point is my common midpoint. So that will take a particular two-way time. Now, if the reflector is steeply dipping towards east, you know, that might also take the same two-way time. Or even if the reflector is like this, this will take even the same two-way time. Okay. So we don't exactly know whether the interface that we are trying to image, what dip does it have? So it can be a vertical plane, it can be a horizontal plane, it can be a vertical plane like this, or it can be any planes which is tangent to this particular ellipse. Okay? It can be any plane which is tangent to this particular ellipse. Okay, with the same two-way time. Okay? Because in one case, the incident ray will be, the incident path will be less, the reflected path will be more. In another case, the incident path and the reflected path will be exactly the same, and in another case the reflected path will be more and the incident path will be less. Okay, so along this sweep ellipse, any point which is tangent to the sweep ellipse would have the same two-way time. What that implies, that I will have, that I will have, you know, I will have, I can have actually, I can have any such, I can have any such orientation of the bed. Okay, theoretically. So this is like a sweep ellipse which is being seen, which is actually being observed, which is being prepared. Okay. Now, of course, now this is not the single trace, right? So there are multiple common midpoints. Okay, there are multiple common midpoints which are present there. Okay? So what do? You actually take this sweep ellipse. Okay, you take that sweep ellipse and then you run it through your actual data. You take that sweep ellipse and you run it through your actual data, and what you observe, that there is the interference between the sweep ellipse and your actual data, and there are places where the amplitude will actually brighten up. The amplitude will actually brighten up, and that is actually your the attitude of the reflector or the bed interface. This is bed A, this is bed B. Okay, so two reflections on the unmigrated data. So this is unmigrated data, as you can see. Reflections are not positioned in the subsurface correctly since they have dip. Now, with the step of migration, what I'm doing in migration, I am essentially taking my sweep ellipse, so which is like a standard. I mean, this is a synthetic seismic data. The sweep ellipse is a synthetic seismic data spread to all possible locations of origin based on the philosophy that I have just explained here. And then you kind of there is constructive interference occurring where the reflections are poorly positioned, and destructive interference dominates where the reflectors are not properly positioned. Okay, so where sorry, the constructive interference occurs when the reflections are properly positioned. Destructive interference dominates where the reflections are not properly positioned. So now, if I now again quickly recap what you first do, you first take your shots, then you do a CMP gather, then you do a move out correction, then after move out correction, you do stacking, okay, and then of course you do migration. Okay, now this migration can be done before stacking, that is called pre-stack depth migration. You can also do it after stacking, that is called post stack depth migration. You can do it okay, now let me just say that here properly. So there are 4 types of migrations. Pre-stack pre-stack time migration, post-stack time migration, pre-stack depth migration, post-stack depth migration. Okay. So what is essentially done, that before, so what is there in a trace? You have here, you have two-way time, and here you have length, right? Now this is in the time domain. You can also convert it into depth domain, where the two-way time is converted to depth using a particular velocity model. Okay. So this is seismic in time domain, and this is seismic in depth domain. Okay. So now in time domain, you can do migration either before stacking or either after stacking. You can also do migration in the depth domain either before stacking or either after stacking. Okay, so basically the steps that you have to take to process your data is first CMP gather, stacking, CMP gather, move out correction, stacking, migration. Okay, and then migration can happen before stacking or after stacking. And then of course there are two types of data. One is where you look at the in the vertical scale, you in the y-axis is in time domain or the y-axis in the depth domain. If the y-axis is in time domain, we call this a time domain data. If the y-axis is in depth domain, you convert it with a the two-way time into depth with a velocity model. That is what we call a depth domain seismic data. Now, so these are the processes that are done. Now you can imagine that you have multiple such layers which have been now converted to a actual real seismic. Okay, so now this is an unmigrated data, and you can see it's very difficult, how these reflectors actually look like after the migration has happened. You can see it's properly positioned actually, and beautiful structures come up. So now, of course, this is what you get so you first acquire your data, then you process your data, and the final step is called seismic interpretation. Okay, so you have your data set in front of you, as a seismic interpreter, as a geologist, as a geophysicist. Now you have to keep on understand the geology from it. Okay, so I'll take you through a couple of seismic sections where we would try to interpret geology from them. Okay, so what are the things that you try to generally map from a seismic section? So determine local geology from the subsurface images, map faults and other structural features, map unconformities and other major stratal surfaces, interpret depositional environment, infer lithophases from reflection pattern velocities, predict ages of the stratal units, examine elements of the hydrocarbon system. Okay, we are not looking into all these features at this particular point, because you need to have knowledge of structural geology and sedimentology and some petroleum geology. But then what we are and that you will gather later in your semesters. But for the timing, we are going to look at some of the seismic sections and broadly interpret them. Okay, so let's start with a very simple one. Okay, so if I ask you, what do you see? And you can very beautifully see, of course, that it's a beautiful anticline and syncline that have developed, right? So these are individual reflectors, which are nothing but their interfaces with different acoustic impedances, right? So you can see this package of the rocks have been beautifully folded. Okay, and you can see this is an anticline, this is a syncline. Okay, perhaps there is an unconformity here because the attitude of the bed is changing. The beds which are below the unconformity, this is perhaps an unconformity. Okay, because the attitude below the beds, are actually folded. Okay, but the attitude of the above the unconformity, the beds are horizontal. There is, perhaps you can observe, a little bit of slope break as well here. So that means perhaps this is the land side of the seismic section, and there is some sort of bathymetric change that you are observing here. Of course, the character of the seismic is different. Okay, so here the seismic character is different. In this package, the seismic character is different. In this package, the seismic character is also different, and that is perhaps due to the lithology. Maybe the type of the rock is actually changing. What changes are happening, we cannot exactly comment with only this knowledge, but then we can at least say that there are some sort of change happening. Now you can see here another seismic image, of course, and you can see here that this particular seismic image also have one well which has been drilled here, Jarboao 1 well, which is on this seismic trace. It's the same area. You can see the development of beautiful fault blocks, okay? And by looking at them, you know that they are normal faults, okay? So these planes are all fault planes, okay? And they are normal faults, and you can immediately recognize that the character of the seismic is very different at the top and at the below. Most likely these are all sedimentary rocks, and these are more metamorphic rocks, okay? So this is what we call as basement, okay? So these basement rocks have been extremely faulted. They are normal faults, and you will see later on that they are called domino type normal faults. There are also some, Horsten graben like faulting happening here as well. So if you don't understand the faulting pattern and everything at this point in time, don't worry, you will learn them later on. But what you can observe, of course, that the seismic character is changing, hence the lithology is changing, and you can map the discontinuities as well. Okay. Now all these sections are of course 2D sections. Okay. So what the explanation that I provided, that these are, like the cross section of the subsurface along these lines. Okay, so this could be an inline, okay, XY inline, or it could be a cross line which is at an high angle or perpendicular to the inline. Okay, now I will not be able to know what is here, okay, because I don't have data. So for that particular case, we actually interpolate them to form a 3D seismic volume out of it. Okay, so the seismic line can be extremely complicated like this. You can here also you can identify at least two types of sedimentary, two types of rock layers. So there is perhaps an unconformity which runs here. Which is as the unconformity is also folded. Yeah, maybe there is another unconformity here, and then you can see there are plenty of faults which have been interpreted. Okay, so as a geophysicist and a geologist, your job, one you can either do a job in acquisition, you can do a job in processing, or you can do a job as a geologist, as a seismic interpreter. So you will be given the seismic lines without these interpretations which have been done later on. Okay, so using your geological knowledge, you have to come up with a possible geological scenario which is responsible in forming this particular sort of lithology and structure. Okay, now if you see here, this is uninterpreted, of course. So you can observe that perhaps, you can very nicely see this faulting going on here. So this layer was here, which has been faulted. So there are plenty of faults which are very steeply dipping here. You can map more faults here as well. Okay. Now you can also see that there is perhaps, and these are all normal faults. Okay. You can perhaps also see that there is a thrust here. Okay, what it means that this set of rocks, these set of rocks, they were kind of here, which has been now thrusted up here. Okay, there is perhaps another thrust here. You can see beautiful folding developed here as well. So you this is what his interpretation is all about. But to do a effective seismic interpretation, of course, you need the knowledge of structural geology, which you don't have at this moment. Understand that we will learn them later on. Okay, here also you can see another seismic section. There is a beautiful fault interpreted, and these are all the horizons. Horizons means the reflectors, which are nothing but the interfaces between different lithologies, and people have identified places where these green areas are the places where hydrocarbon could be, oil or gas could be. Similarly, here it's a very old seismic. The quality of the seismic is not that great, and that is another thing. If you have a poor quality of seismic data, it is always very difficult to actually interpret such seismic. Okay, you can see it's beautiful thrusts. These black lines are thrusts which have been interpreted, and these layers are actually your different lithologies. Okay. Similarly, in the next picture, you can also see the this is what we call a box fold or a double-headed fold. Okay, and this is okay, another beautiful fault and beautiful folds which have been interpreted. And the seismic section can be as interpreted as this one. This is a typical section from a deep water fault belt. What is a deep water fault belt? What are these? These are actually faults. These black lines are actually faults. This line is a horizontal fault which we call a decolma. What are these things? We will discuss later on in our structural geology class. Okay. So the moral of the story is the aim for doing these seismic surveys are to find out your are to find out your subsurface picture. Okay, so I'll stop it here. But before doing that, I let me just answer few questions that were asked by one of you in the WhatsApp group. So let me just answer them, and then I will stop the class, find it out. Okay, I think it is asked by Om. Okay, so the first question is there any correlation between the amplitude of P wave, S wave, and surface wave? Uh, well, there is no direct correlation, but if the earthquake is very strong, the origin of the earthquake is very strong, so the amplitude of the P wave, the S wave, and the surface wave will also increase accordingly. Okay. For a smaller magnitude earthquake, amplitudes are smaller for all three of them. For a larger magnitude earthquake, uh, it's larger for all three of them. Okay. Uh, and what else I can say about that? There is another thing which we call attenuation. Attenuation means the dumping of seismic amplitude with time. Hence, the intensity also decreases with distance from the epicenter. Okay, so the attenuation also would change the amplitude. Okay, now, like since the P wave is faster, it can be recorded earlier, right? So if we can find out the amplitude corresponding to S and surface wave, then maybe we can be okay. No, I don't think you can, because the time difference between P wave arrival and S wave arrival and surface wave arrival is in the range of milliseconds to seconds. Okay. So that will not provide you enough time to be prepared. That's unfortunate, but that's how it is. Do the lava wave and relief wave have some same speed, and the amplitudes uh, are do they exhibit different properties as well? Okay, so the lava wave and relief wave will not coexist together, right? So it's like either there is lava wave at a point in time, or there is relief wave, because the motion of the two waves are very different. Okay, so do they really wave have the same speed and amplitude, or do they exhibit different properties as well? Well, their properties are absolutely different. The ways the waves propagate there is different. So the relay wave velocity and lava wave velocity is quite different. Okay. So now, of course, the lava wave is actually the most devastating wave because of the type of movement that it does. It's not only because of its speed, but because of the type of movement that it has. It actually can destroy. It's the most destructive wave that you can find also within the surface wave domain. Okay, hope that answers the questions. If you have more questions, I'm happy to discuss them in the next class. Okay, thank you very much.